Hello there, and welcome to Nick's Documentaries, where the surface is just the beginning and where the ground beneath your feet tells stories older than mountains, deeper than oceans, more violent than any storm. Tonight, we're not looking up at the stars or out at the horizon. We're going down through the crust, through layers of rock that have witnessed everything, down into the mantle, where stone flows like honey, down to the core, where an ocean of molten iron spins in eternal darkness, generating the magnetic field that shields all life from the solar wind. This is the story of the Earth itself, not the Earth as a stage for life, though life is part of this story, not the Earth as a collection of resources to be extracted, though humans have always dug into it, seeking what's hidden below, but the Earth as it actually is. A living planet, not in the biological sense, but in a geological sense that's just as dynamic, just as active, just as capable of creation and destruction. And before we begin this descent into the planet's heart, into deep time and deeper rock, I'd love to know where in the world you're standing right now. Because wherever you are, you're standing on a story. The ground beneath your feet has a history, a journey that brought it to this exact place, shaped by forces that dwarf anything humans have ever created. Every rock, every grain of sand, every mountain and valley, they all remember. And tonight, we're going to listen. If this kind of exploration speaks to you, if you've ever picked up a rock and wondered where it came from, what forces shaped it, what timescale it represents, I'd be grateful if you tapped like or subscribed. It helps this signal reach others who look at the solid Earth and see not just dirt and stone, but a dynamic system, a history written in minerals and magma, a story that's still being written. And so settle in, feel the ground beneath you, and prepare to descend through layer after layer of rock, through the zones where earthquakes begin and volcanoes are born, through the boundary where the solid meets the liquid, down to the iron core that's been spinning since before the moon existed. We're going to watch the Earth form from dust, watch continents collide and split, watch mountains rise and erode to nothing. We're going to see how the planet breathes, how it remembers, how it connects the deepest interior to the highest atmosphere in ways we're only beginning to understand. The Earth has a memory longer than life itself. It has witnessed everything. And tonight in the quiet, we're going to listen to what it has to say. Let's go back, not just to recorded history, not just to the age of dinosaurs, but to the very beginning, back Sudernt Lu billion years, to a time when there was no Earth at all, no ground to stand on, no sky above, no ocean, no atmosphere, just a cloud of gas and dust spinning in the darkness, one of countless such clouds scattered throughout a young galaxy. This cloud, our solar nebula, was the remnant of previous stars that had lived and died. Everything in it, every atom of hydrogen and helium, every speck of carbon and oxygen and iron, had been forged in the nuclear furnaces of stars or in the explosive deaths of supernovae. We are made of stardust, yes, but so is the entire planet. The iron in your blood and the iron in Earth's core came from the same place, the heart of a dying star that exploded billions of years before our sun was born. And the cloud began to collapse under its own gravity. As it contracted, it spun faster, like a figure skater pulling in their arms. Most of the mass fell toward the center, where pressure and temperature built until nuclear fusion ignited. The sun was born, but not all the material made it to the center. Some remained in a disk around the young star, a swirling disk of dust and gas from which the planets would form. In this disk, dust grains collided, stuck together, grew, from microscopic particles to pebbles, from pebbles to boulders, from boulders to planetesimals, kilometers across. Gravity became significant. The largest bodies attracted more material. growing faster, sweeping up everything in their orbital paths. Within a few million years, a tiny fraction of cosmic time, the disk had sorted itself into a handful of growing planets and countless smaller bodies. An Earth formed in the inner solar system where it was warm enough that only rock and metal could condense. The volatile materials, water and organic compounds and gases, mostly remained farther out, though some would arrive later, delivered by comets and asteroids from the outer system. The young Earth grew through countless collisions, each impact releasing enormous energy, heating the growing planet. These weren't gentle accretions. They were violent collisions at speeds of kilometers per second. Each impact melted the surface, vaporized rock, sent shockwaves through the growing planet. The energy from these collisions, combined with the decay of radioactive elements in Earth's interior, heated the planet until it was completely molten. There was no solid surface, no crust, just an ocean of liquid rock under a thick atmosphere of vaporized silicates and gases. And then came the biggest impact of all. A Mars-sized body, often called Theia, struck the young Earth in a glancing blow. The collision was so violent that it vaporized both the impactor and much of Earth's outer layers. So, a cloud of debris, rock vapor, and molten droplets was thrown into orbit around the Earth. Within a year, perhaps less, this debris had coalesced into the Moon. This collision, called the Giant Impact, was a defining moment in Earth's history. It tilted Earth's axis, giving us seasons. It increased Earth's rotation rate. It stripped away much of the early atmosphere, and it provided enormous additional heat, remelting the entire planet, ensuring that Earth remained molten for millions of years after the impact. But even in this hellish state, the planet was organizing itself. Iron, being denser than rock, sank toward the center. This process, called differentiation, separated Earth into layers based on density. The lightest materials rose to the surface, forming the first protocrust. Intermediate density materials formed the mantle, and the iron, along with some nickel and lighter elements, sank to form the core. This differentiation released even more energy. The friction of iron sinking through rock heated the planet further. For tens of millions of years, Earth was a molten sphere, its surface glowing red, radiating heat into space. No solid string, no solid ground, no water, no life. Just heat and motion and the slow organization of matter into the layered structure that persists to this day. But gradually, inevitably, the planet cooled. Heat radiated into space faster than it was being generated. The surface temperature dropped, and around 7 billion years ago, perhaps a bit earlier, the first solid crust began to form. Not everywhere at once, but in patches, islands of solid rock floating on an ocean of magma. These early crustal fragments didn't last. They were recycled back into the magma, melted, reformed. But eventually, enough heat had been lost that solid crust could persist. This early crust was probably similar to modern basalt, the rock that forms the ocean floor today. Dark, dense, rich in iron and magnesium. It would have been constantly broken and reformed by the motion of the molten rock below, by meteorite impacts that were still frequent, by the heat still radiating from the interior, but it was a beginning, the first solid ground, the first hint that this ball of molten rock might one day become a planet with continents and oceans, with life, and eventually with creatures that could stand on the surface and wonder about the fire below. And the Earth's differentiation into core, mantle, and crust is not just ancient history. It's an ongoing process that still shapes the planet today. The core is still there, still liquid, still hot. The mantle is still slowly flowing. And the crust is still being created and destroyed, constantly renewed by the heat engine that's been running for Sudart low billion years. To understand Earth, you have to understand its structure. The planet is not homogeneous, not uniform throughout. It's layered, like an onion, each layer with distinct properties, distinct compositions, distinct behaviors. These layers weren't designed or planned. They emerged from the simple physics of differentiation, dense materials sinking, light materials rising, organized by gravity into the most stable configuration. Okay, let's start at the center and work our way out. The inner core is a solid sphere of iron and nickel about Arbeck arcers in radius. Despite being at temperatures around Arbeck degrees Celsius, hot enough to melt iron at surface pressure, the inner core is solid because of the immense pressure at Earth's center, over Sandern Luke million times atmospheric pressure. For such pressure, the atoms are forced so close together that they can't move past each other the way they do in a liquid. They're locked in a crystalline structure. This inner core is not static. It's growing very slowly as the planet continues to cool. Iron from the outer core crystallizes onto the inner core's surface, adding about 1 millimeter to its radius every 1,000 years or so. This might not sound like much, but over billions of years, it adds up. The inner core may have been much smaller in the past, perhaps even non-existent when the Earth was younger and hotter. Okay. Surrounding the inner core is the outer core, a shell of liquid iron and nickel, about centimeters kilometers thick. The temperature here is similar to the inner core, but the pressure is slightly lower, low enough that the iron remains liquid. This liquid iron is not still, it's in constant motion, driven by convection currents. Hot iron rises from near the inner core, cools as it approaches the mantle above, and sinks back down. This motion, combined with Earth's rotation, generates electric currents in the conducting iron, and these electric currents generate Earth's magnetic field. This magnetic field is crucial. It extends far beyond the surface, creating a protective bubble called the magnetosphere that shields Earth from the solar wind, a stream of charged particles flowing from the sun. Without this magnetic field, the solar wind would strip away Earth's atmosphere, making the surface uninhabitable. Mars, which lost its magnetic field billions of years ago, shows us what happens. Its atmosphere was stripped away. Its surface became a frozen desert. The motion of the outer core is complex, turbulent, not fully understood. The magnetic field it generates is not stable. The field strength varies. The magnetic poles wander. And periodically, every few 100,000 years on average, the entire field flips north, becoming south, and south, becoming north. These reversals are recorded in rocks that contain magnetic minerals, creating a record of Earth's magnetic history going back billions of years. Above the core is the mantle, a thick shell of rock about 2 kilometers thick, making up about 500 basus of Earth's volume. The mantle is solid, but not solid in the way we usually think of rock. It's under enormous pressure and temperature, conditions that allow it to flow very slowly, like honey or wax, over long time scales. This flow is called convection, and it's driven by heat from the core below and from the decay of radioactive elements within the mantle itself. Hot rock rises from deep in the mantle, moves horizontally beneath the crust, cools, and sinks back down. This process is incredibly slow, taking millions of years to complete a single cycle. But over geological time, this convection has profound effects. It drives plate tectonics, the movement of Earth's crustal plates. It brings heat to the surface, manifesting as volcanism and geothermal activity. It recycles crustal material back into the deep interior, erasing the geological record. The mantle is not uniform. The upper mantle, down to about kilometers depth, is distinct from the lower mantle below it. There's a transition zone between them where the crystal structure of the minerals changes, becoming denser, adapting to the higher pressure. These changes in crystal structure affect how the rock flows, creating layering in the convection patterns. The upper mantle includes the asthenosphere, a particularly weak layer where the rock is close to its melting point, making it especially prone to flow. Above the asthenosphere is the lithosphere, the rigid outer shell that includes the crust and the uppermost mantle. The lithosphere is broken into plates, the tectonic plates that move across the surface, carrying continents and ocean floor, colliding and separating, creating mountains and ocean trenches. And finally, the crust, the thin skin on which all life exists. The crust is incredibly thin compared to the layers below, just 2 to 3 kilometers thick, less than bifundra E of Earth's radius. But it's geologically diverse, chemically complex, constantly being created and destroyed. There are 2 types of crust. Oceanic crust, which forms the ocean floor, is thin, about 2 kilometers thick, dense, young, composed mainly of basalt. It's constantly being created at mid-ocean ridges, where mantle rock rises, partially melts, and erupts as lava. And it's constantly being destroyed at subduction zones, where it sinks back into the mantle. Continental crust is thicker, since 2 kilometers, on average less dense, much older, composed of a variety of rock types, but dominated by granite and related rocks. Continental crust is too buoyant to be subducted. Once formed, it persists, though it can be deformed, metamorphosed, eroded, and built up through the addition of new material. This layered structure, from the iron core to the silicate crust, defines how Earth works. The heat flowing from the interior drives everything: plate tectonics, volcanism, mountain building, the rock cycle. Without this internal heat, Earth would be a dead world, geologically inert like the moon, with no tectonic activity, no volcanism, no magnetic field. The internal heat is what makes Earth alive, geologically speaking, and that heat is the remnant of Earth's violent birth, supplemented by the decay of radioactive elements, slowly leaking away over billions of years. The Earth is cooling. It has been since it formed. Billions of years from now, the core will solidify completely, the mantle will become too stiff to convect, and Earth will join the ranks of dead worlds. But that's far in the future. For now, the internal fire still burns, and the planet remains dynamic, active, alive in its geology. Now let's come back to the surface, to the thin skin we inhabit, and understand how it moves. Because the most revolutionary insight in geology, the idea that changed everything we thought we knew about the planet, is this: the surface moves. The continents drift, the ocean floor spreads. The crust is not permanent. It's constantly being created, destroyed, and rearranged by forces from deep below. And this idea, called plate tectonics, is young by scientific standards. The theory was only accepted in the Licursus, though the observations that led to it go back further. In the early Earth century, people noticed that the continents looked like they might fit together, like pieces of a jigsaw puzzle. South America and Africa particularly, their coastlines mirror each other across the Atlantic. Fossils of the same species were found on both sides of the ocean. Rock formations matched across continents, now separated by thousands of kilometers of ocean. In Ishar, Alfred Wegener proposed continental drift, the idea that the continents had once been joined in a supercontinent and had since moved apart. He was right, but he couldn't explain the mechanism. How could continents plow through the ocean floor? The idea seemed physically impossible. For decades, continental drift was dismissed by most geologists, but evidence accumulated. In the Licursus and Licursus, ships equipped with new instruments mapped the ocean floor in detail for the first time. They discovered a system of underwater mountain ranges, mid-ocean ridges, running through all the ocean basins. They found that the ocean floor was young, nowhere older than about million years, while the continents contained rocks billions of years old. They discovered that the ocean floor had magnetic stripes, alternating bands of rock with opposite magnetic orientations, recording the reversals of Earth's magnetic field, and they found deep ocean trenches where the ocean floor seemed to plunge back into the interior. Earthquakes were concentrated at these trenches and along the mid-ocean ridges and along certain fault lines on continents. Volcanism followed patterns, chains of volcanoes associated with the trenches, volcanic ridges along the mid-ocean ridges, and all these observations came together in the theory of plate tectonics. The lithosphere, the rigid outer shell, is broken into plates. These plates move across the surface, driven by convection in the mantle below. At mid-ocean ridges, plates diverge, and new oceanic crust is created as mantle rock rises and melts. At subduction zones, plates converge and oceanic crust sinks back into the mantle. At transform faults, plates slide past each other, and where continental plates collide, mountains are built. The rates of motion are slow by human standards, a few centimeters per year, about the rate your fingernails grow. But over millions of years, these motions add up. Continents that were once joined separate and drift thousands of kilometers apart. Ocean basins open and close. Mountain ranges rise and erode away. The map of the Earth is constantly being redrawn. Okay, let's follow the journey of oceanic crust to understand the cycle. Deep in the mantle, hot rock rises, creating an upwelling. This rising rock eventually reaches the base of the lithosphere beneath a mid-ocean ridge. The pressure decreases as it rises, causing it to partially melt. This magma, being less dense than the solid rock around it, rises further, eventually erupting on the ocean floor as lava. The lava cools rapidly in the cold ocean water, solidifying into pillow basalts, bulbous shapes characteristic of underwater eruptions. This new rock becomes part of the ocean floor. As more magma erupts, it pushes the older rock aside, creating new crust in a continuous process. The mid-ocean ridges are spreading centers, where new oceanic lithosphere is constantly being created. The newly formed oceanic crust moves away from the ridge, carried by the motion of the plate. As it moves, it cools and contracts, becoming denser. It also accumulates a thin layer of sediment, the remains of microscopic organisms that lived in the surface waters and sank to the bottom when they died, along with dust blown from continents and volcanic ash. Eventually, this oceanic lithosphere reaches a subduction zone where it meets another plate. Because it's cold and dense, it sinks back into the mantle, diving beneath the other plate at an angle. The subducting slab descends into the mantle, heating up as it goes. Water trapped in the minerals of the altered ocean crust is released. This water rises into the mantle wedge above the subducting slab, lowering the melting point of the rock there, causing it to melt. This magma rises, eventually erupting at the surface to form a chain of volcanoes parallel to the trench. If the subduction zone is in the ocean, these volcanoes form an island arc, like Japan or the Aleutians. If the subduction zone is at the edge of a continent, the volcanoes form a continental arc, like the Andes or the Cascades. The subducting slab continues to descend, eventually reaching the mantle's transition zone at about kilometers depth. Some slabs stall here, piling up. Others penetrate into the lower mantle, descending all the way to the core mantle boundary. Eventually, the slab material is heated and assimilated into the mantle, completing the cycle. Rock that was once at the surface is recycled into the deep interior, its history erased, only to rise again millions of years later as part of a new upwelling. This cycle, from creation at mid-ocean ridges to destruction at subduction zones, is called the Wilson cycle, named after the geophysicist J. Tuzo Wilson. It typically takes about sembite million years to complete, which is why the oldest ocean floor is only about million years old. Everything older has been subducted and recycled, but continental crust is different. It's too buoyant to subduct. When two plates with continental crust collide, neither can sink into the mantle. Instead, they crumple, deform, build mountains. The Himalayas are the result of the Indian plate colliding with the Eurasian plate. The collision is still ongoing, and the mountains are still rising, even as erosion wears them down. Continental collisions create supercontinents, massive landmasses formed when smaller continents are welded together. The most recent supercontinent was Pangaea, which existed about sembite million years ago. Before Pangaea, there was Rodinia about a billion years ago. And before that, others going back into the deep past, but supercontinents don't last. They insulate the mantle beneath them, trapping heat. Eventually, the trapped heat causes the mantle to upwell beneath the supercontinent, rifting it apart. New ocean basins open. The continents drift apart, and the cycle begins again. We're currently in a dispersed phase. The continents are scattered around the globe, but mantle convection continues. Plates continue to move. And eventually, hundreds of millions of years from now, the continents will collide again, forming a new supercontinent. And then that supercontinent will rift apart, on and on, as long as Earth's interior remains hot enough to drive convection. And plate tectonics is not just an interesting geological process, it's fundamental to Earth's habitability. It recycles carbon, pulling it into the mantle at subduction zones and releasing it at volcanoes, regulating atmospheric company R levels over millions of years. It creates diverse environments, from deep ocean trenches to high mountains, driving evolution. It generates Earth's varied topography, which affects climate, ocean currents, and the distribution of life. Without plate tectonics, Earth would be a very different world. No mountain ranges, no ocean trenches, a much smoother surface, and probably no life, at least not life as we know it. Plate tectonics is what makes Earth unique among the rocky planets we know. It's the signature of a planet still burning with internal fire. Stand at the base of a mountain and look up. The peak seems eternal, unchanging, a permanent feature of the landscape. But mountains they are born, they grow, they age, and they die, eroded grain by grain back to the sea from which the rock originally came. Mountains are monuments to geological time, to forces that operate on scales almost incomprehensible to human perception. Every major mountain range on Earth is the result of plate tectonics. The Himalayas, the Andes, the Alps, the Rockies, all were built by the collision or convergence of tectonic plates. The details differ, but the basic process is the same. When plates converge, the crust is compressed, thickened, forced upward. The Himalayas are the tallest mountain range on Earth, home to Mount Everest and the other 8,000ers. They formed when the Indian plate, which had been an island continent, collided with the Eurasian plate about million years ago. The collision continues today. India is still pushing northward at about centimeters per year. The Himalayas are still rising, though erosion removes material almost as fast as tectonics adds it. The rocks at the summit of Everest are marine limestone, formed from the shells of sea creatures that lived in a tropical ocean. This ocean, called the Tethys, once separated India from Eurasia. When the continents collided, the ocean floor was caught between them, crumpled, folded, thrust upward. Rock that formed on the seafloor now sits at about 6 meters above sea level, the highest point on Earth's surface. The Andes formed through a different process. They're a continental arc built by subduction of the Nazca Plate beneath the South American plate. As the oceanic plate subducts, it melts, and the magma rises to form volcanoes. But the Andes are more than just a chain of volcanoes. The compression from the subduction also thickens the continental crust, uplifting the entire region. The result is a massive mountain range stretching T-ling kilometers along the western edge of South America, studded with active volcanoes. The Alps formed when the African plate collided with the Eurasian plate, closing the Tethys Ocean and crumpling the crust between them. The Rockies formed from a combination of processes, including the subduction of oceanic plates beneath North America and the uplift caused by mantle dynamics. Each mountain range has its own story, its own particular history of plate motions and crustal deformation, but building mountains is only half the story. The other half is erosion, the slow dismantling of mountains by weathering and transport. The moment a mountain range begins to rise, it begins to erode. Rain falls on the peaks, seeps into cracks, freezes, expands, splitting the rock. Temperature changes cause thermal stress, fracturing the rock. Chemical weathering, the reaction of rock minerals with water and atmospheric gases, weakens the rock, turning solid minerals into clay. Gravity pulls the loosened material downslope. Water carries it, grinding it against other rocks, abrading everything it touches. The fragments are transported by streams and rivers, carried from the mountains to the lowlands, eventually to the sea. Senki. Along the way, the fragments are ground finer and finer, from boulders to cobbles to pebbles to sand to silt to clay. This process is relentless. It never stops. Over millions of years, entire mountain ranges can be eroded down to their roots, reduced to low hills, eventually to plains. The Appalachians, once as high as the Himalayas when they formed about C/Bashar's million years ago, are now much lower, worn down by hundreds of millions of years of erosion. The sediment eroded from mountains doesn't disappear. It's deposited in basins, in river deltas, on continental shelves, in the deep ocean. Layer upon layer accumulates, burying older sediments, compressing them, turning them into sedimentary rock. These rocks preserve a record of erosion, climate, and life. Each layer is a page in Earth's history book. But this sedimentary rock doesn't stay at the surface forever. Plate tectonics ensures that it too will be recycled. Continental collisions can thrust sedimentary rocks deep into the crust, where heat and pressure transform them into metamorphic rocks. Subduction carries sediments back into the mantle, and weathering and erosion break down the sedimentary rocks, starting the cycle again. This is the rock cycle, one of the fundamental concepts in geology. Igneous rocks formed from cooling magma are weathered and eroded to form sediments. Sediments are lithified into sedimentary rocks. Sedimentary rocks, if buried deeply enough, are metamorphosed. And metamorphic rocks, if buried even more deeply or carried into the mantle, melt, forming magma that can erupt to form new igneous rocks. Around and around, driven by Earth's internal heat and by the sun's energy driving weathering and erosion. Mountains, then, are temporary features. They rise and fall over geological time. The oldest rocks in mountain ranges often show evidence of previous mountain building events, earlier collisions, earlier periods of deformation and metamorphism. The crust has memory. It records its history in the structures and minerals of its rocks. John McPhee, in his book Annals of the Former World, describes looking at road cuts, the cliffs of exposed rock along highways, and seeing deep time revealed. The layers, the folds, the faults all tell stories of ancient environments, ancient forces, ancient geographies. A road cut that you drive past in seconds might represent 100 million years of Earth history compressed into a few dozen meters of rock. This perspective, understanding geological time, is perhaps the most profound shift that geology offers. Mountains that seem permanent are ephemeral on geological timescales. Continents that seem fixed have drifted thousands of kilometers. Rock that seems solid has flowed. The Earth's surface is dynamic, constantly changing, constantly renewed. Nothing is permanent except change itself, and this change is ongoing. Mountains are rising right now. The Himalayas grow a few millimeters per year. Erosion removes material right now. Rivers carry millions of tons of sediment to the sea every year. Earthquakes occur, faults slip. The crust deforms. We live on a dynamic planet, and if we pay attention, if we look at the right time scale, we can see it moving. Let's talk about fire. Not the chemical combustion of organic matter, but the deep fire, the molten rock that rises from the mantle, that erupts at the surface, that builds volcanoes and reshapes the crust. Volcanism is one of the most direct manifestations of Earth's internal heat. It's the planet bleeding, releasing pressure, venting the heat that would otherwise accumulate in the interior. Volcanoes occur where magma reaches the surface, but not all magma makes it. Most magma generated in the mantle solidifies before reaching the surface, forming plutonic rocks, large bodies of igneous rock like granite batholiths that cool slowly at depth. Only a fraction of magma erupts, but when it does, the results can be spectacular and catastrophic. There are several settings where volcanoes form. The most common is at subduction zones, where one tectonic plate descends beneath another. The subducting plate carries water, locked in minerals that formed when the ocean floor was altered by seawater. As the plate descends and heats up, this water is released. It rises into the overlying mantle wedge, lowering the melting point of the rock there, causing it to melt. The resulting magma is often andesitic or dacitic in composition, intermediate between basalt and granite, viscous, gas-rich. When this magma erupts, the gases trapped in it expand explosively, fragmenting the magma into ash and pumice, creating explosive eruptions. These are the volcanoes that make headlines, the ones that produce towering ash columns, pyroclastic flows, and devastating lahars. Mount St. Helens, Mount Pinatubo, Krakatoa, Mount Vesuvius. These are all subduction-related volcanoes. Their eruptions have killed thousands, disrupted global climate, and left scars on human history. Vesuvius buried Pompeii and Herculaneum in Caesarjol AD, preserving them under meters of ash and pumice. Krakatoa's Ichen Babai Badarsan eruption was one of the loudest sounds in recorded history, heard thousands of kilometers away. Pinatubo's Ichenju Baiju eruption injected so much sulfur dioxide into the stratosphere that it cooled global temperatures by about 0.5 degrees Celsius for 2 years. But subduction zones aren't the only source of volcanism. Mid-ocean ridges, where tectonic plates diverge and new ocean floor is created, are sites of extensive volcanic activity. Most of this occurs underwater, hidden from view, but it's the most voluminous volcanic process on Earth. Along the ling kilometers of mid-ocean ridges, magma rises continuously, erupting as pillow lavas, building new ocean crust. The lava at mid-ocean ridges is basaltic, low in silica, low in viscosity, low in gas. It erupts relatively quietly, oozing out rather than exploding. Underwater, the cold water quenches the lava rapidly, forming the characteristic pillow shapes. These eruptions support unique ecosystems, the hydrothermal vent communities where chemosynthetic bacteria form the base of the food web. Then there are hotspots, places where plumes of hot mantle rock rise from deep in the interior. possibly from the core mantle boundary. These plumes are stationary relative to the moving tectonic plates above them. As a plate moves over a hotspot, the hotspot burns through the plate, creating a volcano. As the plate continues to move, the volcano is carried away from the hotspot and becomes extinct. A new volcano. The result is a chain of volcanoes, progressively older as you move away from the hotspot. Hawaii is the classic example. The Hawaiian Islands are the tops of massive shield volcanoes built over the Hawaiian hotspot. The Big Island, Hawaii, is currently over the hotspot and has active volcanoes. As you move northwest along the chain, the islands get older. Kauai is about 1 million years old. Beyond Kauai, the chain continues as a series of seamounts, extinct volcanoes that have subsided below sea level. The entire chain, including the Emperor seamounts that bend to the north, stretches over, low, kilometers, recording the motion of the Pacific Plate over the past Basher's million years. Hotspots have produced some of the most massive volcanic features on Earth. The Deccan Traps in India, the Siberian Traps in Russia, and the Columbia River basalts in the northwestern United States are all flood basalts, vast outpourings of lava that covered hundreds of thousands of square kilometers. The Siberian Traps eruption, about Arbak Wushurar million years ago, coincided with the Permian-Triassic mass extinction, the worst extinction event in Earth's history. The eruption released enormous amounts of carbon dioxide and sulfur dioxide, causing global warming and ocean acidification, killing perhaps bifurcations of all species. Volcanic eruptions can affect global climate. Large explosive eruptions inject sulfur dioxide into the stratosphere, where it forms sulfate aerosols that reflect sunlight, cooling the planet. The eruption of Mount Tambora in Ichen Babai Isherwu caused the year without a summer in Ichen Babai Isherloop, leading to crop failures and famine in Europe and North America. Smaller eruptions have smaller effects, but the cumulative impact of volcanism on climate is significant. But volcanism also has benefits. Volcanic ash weathers to form fertile soil. Volcanic islands provide habitat and resources. Volcanism releases gases from Earth's interior, including water vapor and carbon dioxide, that have accumulated over geological time to form the atmosphere and oceans. Without volcanism, Earth might be a dry, airless world like the Moon, and volcanism is a window into the interior. Volcanic rocks carry information about the composition of the mantle, about the processes occurring at depth. Diamonds, formed deep in the mantle under enormous pressure, are sometimes carried to the surface in volcanic eruptions, providing samples of rock from depths we can never reach by drilling. Volcanoes remind us that the Earth is not a cold, dead rock. It's active, dynamic, capable of immense violence. The fire below is always there, waiting. In some places it breaks through, building mountains, reshaping the surface, venting heat and gas from the deep interior. Volcanism is the planet breathing, releasing the pressure that builds within. Every eruption is a reminder that beneath the solid crust, beneath the mountains and the ocean floor, there's heat, there's motion, there's an energy that has persisted since the planet's formation. The volcanoes we see today are just the latest in a chain of volcanic events stretching back billions of years. The earliest Earth was entirely volcanic, its surface an ocean of magma. As the planet cooled, volcanism became more localized, more episodic, but it never stopped. Every type of rock we see today, every mineral formation, every mountain range, traces its origin back to volcanism in some form. Understanding volcanoes means understanding risk. About babat million people live within ebat kilometers of an active volcano. The signs of an impending eruption, earthquake swarms, ground deformation, gas emissions, These are closely monitored at dangerous volcanoes, but prediction remains imperfect. Some eruptions come with clear warning, others happen with little notice. The ground beneath our feet is not as stable as we like to think. If volcanism is the earth bleeding, then earthquakes are the earth cracking. They're the sudden release of elastic energy that has been building up in the crust, stored in rocks that are being deformed by tectonic forces. For years, decades, sometimes centuries, the rocks bend and compress and stretch, accumulating strain. And then, suddenly, they break. The stored energy is released in seconds, radiating outward as seismic waves that shake the ground. And most earthquakes occur at plate boundaries. At subduction zones, the descending plate sticks against the overriding plate, locked by friction. But the plates continue to move, driven by forces from deep in the mantle. Stress builds at the interface. Eventually, the stress overcomes the friction. The plates slip suddenly, catastrophically. The overriding plate rebounds upward and outward. If this happens beneath the ocean, it can displace enormous volumes of water, generating a tsunami. The Artsenlingisuri Tohoku earthquake off the coast of Japan was a magnitude, Jodian-e, one of the most powerful earthquakes ever recorded. The Pacific plate lurched beneath the North American plate by as much as meters in some places. The seafloor was uplifted by several meters over an area of hundreds of kilometers. The resulting tsunami devastated the Japanese coast, killing over Sturvor-Ling people and triggering the Fukushima nuclear disaster. At transformed boundaries where plates slide past each other horizontally, earthquakes are also common. The San Andreas Fault in California is perhaps the most famous example. The Pacific plate is moving northwest relative to the North American plate at about wu centimeters per year. But the motion isn't smooth. Sections of the fault are locked, building up stress. When they finally slip, the result is a major earthquake. The Ichenjolbite Linglu San Francisco earthquake, estimated at magnitude, Chidarju, ruptured c kilometers of the fault. The ground shifted by up to lookometers in places. The shaking destroyed much of San Francisco, and the fires that followed burned for days. Earthquakes on the San Andreas are inevitable. The plates will continue to move, stress will continue to build, and eventually the fault will slip again. But earthquakes also occur within plates, far from boundaries. These intraplate earthquakes are less common, but can be devastating because they often occur in areas not prepared for them. The New Madrid earthquakes of Ichen Babait Isur I Fu Ichen Babait Ishirar, centered in Missouri, were among the most powerful earthquakes in U.S. history. Estimated at magnitudes around Chito Ba, they were felt over an enormous area, ringing church bells in Boston, over loop kilometers away. The causes of intraplate earthquakes are not fully understood. Ancient faults, weak zones in the crust from previous tectonic episodes, can be reactivated by current stresses. The weight of sediments, the rebound of the crust after ice sheets melt, even human activities like reservoir impoundment and fluid injection can trigger earthquakes. Seismic waves come in several types. Primary waves, or P waves, are compressional waves that travel through both solid and liquid. They're the fastest seismic waves, arriving first at seismometers. Secondary waves, or S waves, are shear waves that only travel through solid material. They're slower than P waves, but often carry more energy. Surface waves travel along the Earth's surface and are responsible for most of the damage in earthquakes. By studying seismic waves, geologists have learned an enormous amount about Earth's interior. When an earthquake occurs, seismic waves radiate in all directions. They travel through the Earth, refracting and reflecting at boundaries between different materials. Seismometers around the world record these waves, and by analyzing the arrival times and characteristics of different wave types, scientists can infer the structure of the interior. And this is how we know the outer core is liquid. S waves don't pass through it, creating a shadow zone on the opposite side of the Earth from any earthquake. This is how we know the inner core is solid. P waves that pass through it are refracted in ways consistent with a solid. This is how we map the boundaries between the crust, mantle, and core, and how we detect anomalies like subducted slabs or mantle plumes. The Earth is ringing like a bell, constantly excited by earthquakes. Even when there's no major earthquake, the planet is always vibrating slightly, a phenomenon called microseismic noise, caused by ocean waves, wind, and human activity. By listening to these vibrations, by deploying networks of sensitive seismometers, we can create increasingly detailed images of Earth's interior, mapping the variations in temperature, composition, and flow that drive everything happening at the surface. Earthquakes remind us of the power stored in the crust, the energy that accumulates grain by grain as plates move. They remind us that the solid Earth is not truly solid, not on geological timescales, not under geological stresses. Everything is moving, bending, breaking, reforming. The ground beneath us is dynamic, and occasionally it reminds us violently of that fact. Let's descend now to the deepest places on Earth's surface, the ocean trenches where tectonic plates plunge back into the mantle. These are the lowest points on the planet, gouges in the seafloor that reach depths of 3 kilometers, deeper than Mount Everest is tall. They're places of immense pressure, complete darkness, and bizarre life. The Mariana Trench in the Western Pacific is the deepest, reaching Sir Joules meters at Challenger Deep. To put this in perspective, if you placed Mount Everest at the bottom of Challenger Deep, its peak would still be over R kilometers underwater. The pressure at this depth is over E Ling times atmospheric pressure, about Sirleuk Ling pounds per square inch. Water doesn't compress much, but at these pressures it becomes noticeably denser. The ocean trenches form at subduction zones where oceanic lithosphere, old and cold and dense, sinks back into the mantle. The trench marks the line where the plate bends downward, flexing as it begins its descent. This flexing creates normal faults in the outer part of the plate, which is in tension, and thrust faults in the inner part, which is in compression. As the plate descends, it drags sediments with it, sediments that have accumulated on the ocean floor over millions of years. Some of this sediment is scraped off and accreted to the overriding plate, forming an accretionary wedge, a chaotic mass of deformed sediments and oceanic crust. Some sediment is carried down with the subducting plate into the mantle. The subducting plate doesn't descend smoothly. It sticks and slips, generating earthquake. These earthquakes define the Wadati-Benioff zone, a band of seismicity that extends from the trench down into the mantle, outlining the subducting slab. Earthquakes in this zone can occur at depths of Chibyte kilometers or more, far deeper than earthquakes elsewhere. Deep earthquakes are strange. At such depths, the pressure is so high that rocks can't fracture in the normal way. Instead, deep earthquakes are thought to result from phase transformations, sudden changes in the crystal structure of minerals that release energy. As the slab descends and heats up, minerals transform to denser structures, and these transformations can be abrupt enough to generate seismic waves. The fate of the subducted material has been debated. Some slabs seem to stall at the Loop-Byte-Lickers kilometer discontinuity, the boundary between the upper and lower mantle, piling up there. Others penetrate into the lower mantle, descending all the way to the core mantle boundary. Seismic tomography, which uses seismic waves to image the interior much like a CT scan images the body, has revealed slabs extending deep into the mantle. And at the core mantle boundary, some Arjubyte kilometers down, the coldest slabs may form a slab graveyard, piled up at the base of the mantle. Eventually, this material heats up, becomes less dense, and rises again as part of mantle plumes. The timescale for this overturn is uncertain, but it may be hundreds of millions to billions of years. Material from Earth's surface, carried down by subduction, may take this long to return. But ocean trenches are not lifeless. Despite the pressure, the cold, the darkness, life exists even in Challenger Deep. In Ichenjubek Liquors, Jacques Picard and Don Walsh descended to the bottom in the bathyscaphe Trieste. They reported seeing a flatfish, though this has been questioned. More recent expeditions have found amphipods, sea cucumbers, and microbial mats thriving in these extreme conditions. By about 1 billion years ago, significant volumes of continental crust existed, gathered into small protocontinents called cratons. These cratons, though small by modern standards, were stable, resistant to deformation. They've been the cores around which later crust accumulated, welded together during continent collisions, enlarged by the addition of newer crust at their margins. The rocks of the shields tell stories of ancient mountain building, ancient collisions, ancient volcanism, greenstone belts, sequences of volcanic and sedimentary rocks metamorphosed to green minerals are common in shields. They preserve evidence of ancient seafloor volcanism, ancient sedimentary basins, environments that no longer exist but that were common in the Archean Eon, C2 Ardent Wove billion years ago. The shields also contain banded iron formations, layers of iron oxide alternating with layers of silica, formed when iron dissolved in the ocean precipitated out. These formations are found worldwide in rocks about Ardent Su to Eternbat billion years old. Their formation is linked to the Great Oxidation Event, when photosynthetic cyanobacteria began producing oxygen, changing the chemistry of the ocean and atmosphere. And before the Great Oxidation Event, Earth's atmosphere contained little free oxygen. The ocean was anoxic, rich in dissolved iron. Cyanobacteria, which had evolved perhaps 10 billion years ago or earlier, performed oxygenic photosynthesis, releasing oxygen as a waste product. At first, this oxygen reacted with dissolved iron and other reduced substances, but eventually, the oxygen began to accumulate in the atmosphere. This was a crisis for anaerobic life, which found oxygen toxic. Many lineages went extinct or retreated to anoxic refugia, but it was also an opportunity. Oxygen enables aerobic respiration, a much more efficient way to extract energy from organic matter. The rise of oxygen set the stage for the evolution of complex life, though that wouldn't happen for another billion years. The banded iron formations are a record of this transition, a record written in rock, visible in the shields. They're also economically important. Much of the world's iron ore is mined from these formations. The ancient ocean's chemistry, shaped by early life, shaped by the interplay of biology and geology, provides resources we use to. The continental shields are not static. They've been deformed, faulted, intruded by later magmas. But they've survived. They're the pieces of Earth's crust that have resisted recycling, that have remained at the surface for billions of years. They're the foundation on which the continents are built, the anchor points in the ever-shifting mosaic of tectonic plates. And we've talked about how rocks form, how they're destroyed, how they're transformed. Now let's step back and see the big picture, the rock cycle, the continuous transformation of Earth's materials driven by the planet's internal heat and by solar energy. Start with magma. Magma rises from the mantle, either at mid-ocean ridges, at subduction zones, at hotspots, or in other settings. When it cools, it forms igneous rock. If it cools quickly at the surface, it forms extrusive igneous rock like basalt or andesite. If it cools slowly at depth, it forms intrusive igneous rock like granite or gabbro. This igneous rock, once at or near the surface, is exposed to weathering. Physical weathering breaks it into fragments. Chemical weathering alters its minerals, turning feldspars into clay, dissolving some components, leaving others behind. The products of weathering are transported by water, wind, or ice, and deposited elsewhere as sediment. Sediment accumulates in layers. Over time, buried under more sediment, compacted and cemented by minerals precipitating from groundwater, it lithifies into sedimentary rock. Sandstone, shale, limestone, these are sedimentary rocks formed from particles or precipitates deposited in ancient environments. But sedimentary rock at the surface can also be weathered and eroded, producing sediment again. Or it can be buried, carried deeper into the crust by tectonic processes. As it's buried, temperature and pressure increase. At depths of tens of kilometers, under conditions of elevated temperature and pressure, but below the melting point, the rock undergoes metamorphism. Metamorphism changes the mineral content and texture of the rock without melting it. Shale metamorphoses to slate, then to schist, then to gneiss as temperature and pressure increase. Limestone metamorphoses to marble. Sandstone metamorphoses to quartzite. The original sedimentary or igneous rock is transformed, its history partially erased, overwritten by the conditions it now experiences. If buried even deeper, or if affected by fluids that lower the melting point, the rock melts, forming magma. This magma may rise, intruding into the crust or erupting at the surface, and the cycle begins again. Igneous to sedimentary to metamorphic to igneous, around and around, driven by plate tectonics, driven by the heat flowing from Earth's interior. But the rock cycle is not a simple loop. There are shortcuts, branches, complications. Igneous rock can be metamorphosed directly without first becoming sedimentary. Metamorphic rock can be uplifted and eroded, becoming sediment. Sedimentary rock can melt without going through a metamorphic stage if temperatures are high enough. And not all rock participates in the cycle at the same rate. Oceanic crust is recycled every million years or so, subducted back into the mantle. But continental crust, being less dense, is more likely to stay at the surface, to be reworked repeatedly. Some continental rocks are billions of years old, surviving multiple cycles of erosion, deposition, metamorphism. This recycling is not perfect. Some information is preserved. Zircon crystals, for instance, are incredibly resistant to weathering and to high temperatures. They can survive multiple cycles of the rock cycle, carrying isotopic signatures from their original formation. By studying zircons, geologists can learn about rocks that no longer exist, eroded away billions of years ago. Isotopes are key to reading Earth's history. Different elements have different isotopes, atoms with the same number of protons, but different numbers of neutrons. Some isotopes are radioactive, decaying at known rates into other isotopes. By measuring the ratios of parent and daughter isotopes in a rock, we can determine when the rock formed, when it was metamorphosed, when it cooled below certain temperatures. A radiometric dating has revealed Earth's age, Ursi billion years, determined from the oldest meteorites, and which formed at the same time as the solar system. It has revealed the age of the oldest rocks, the oldest zircons, the timing of major geological events. It has given us a timeline, a chronology, allowing us to place rocks and events in sequence to understand the history of the planet. But reading this history requires care. Rocks can be reset by later events. Metamorphism can reset isotopic clocks. Weathering can remove or add elements, altering isotopic ratios. Interpreting ages requires understanding the rock's history, the events it has experienced, the processes that have affected it. Okay? The rock cycle is the grand recycling system of the solid Earth. It ensures that nothing is permanent, that everything is in flux. Mountains erode, their particles are deposited as sediment, lithified, buried, metamorphosed, perhaps melted, perhaps erupted as lava, building new mountains. The surface is constantly renewed, constantly reshaped, constantly recycled. And yet, despite this recycling, the Earth remembers. Not perfectly, not completely, but in fragments, in isotopes, in structures, in minerals that resist destruction. The rock cycle creates a palimpsest, a manuscript that has been written on, erased, and written on again, but where traces of earlier texts remain visible. Reading this palimpsest is the challenge and the joy of geology. Earth is not just rock and metal. It's also water and air and carbon, cycling between reservoirs, driven by geological processes and by life. These cycles operate on timescales from days to billions of years, connecting the deep interior to the atmosphere, the ocean to the crust, life to the lithosphere. And let's start with water. Earth is sometimes called the blue planet because of its abundant surface water, but most of Earth's water is not at the surface. It's locked in minerals in the mantle, stored as hydroxyl groups in the crystal structures of minerals like amphibole and serpentine. The mantle may contain several times as much water as all the oceans combined. This water cycles through the mantle. At subduction zones, water in the altered oceanic crust and in sediments is carried down. As the slab heats, the water is released, rising into the mantle wedge, causing melting, leading to volcanism. Some water escapes at volcanic arcs, released as steam and incorporated into hydrothermal fluids. But some water may be carried deeper, into the transition zone, into the lower mantle. At mid-ocean ridges, water circulates through the newly formed oceanic crust, heated by magma below, emerging at hydrothermal vents. This circulation alters the basalt, hydrating it, storing water in minerals. When this crust is subducted millions of years later, it carries water back into the mantle, completing a cycle that takes hundreds of millions of years. It was equally complex. Carbon is stored in carbonate rocks, in organic matter, in the atmosphere and ocean, and in the mantle. Plate tectonics drives the long-term carbon cycle, regulating atmospheric company, or over millions of years. Here's how it works. Carbon dioxide in the atmosphere reacts with rainwater, forming carbonic acid. This acid weathers silicate rocks, dissolving them, releasing calcium and bicarbonate ions that wash into the ocean. In the ocean, organisms use these ions to build shells and skeletons of calcium carbonate. When they die, their shells accumulate on the seafloor, forming limestone. This process removes company R from the atmosphere, locking it in carbonate rocks. Over millions of years, enormous amounts of carbon are stored this way. But plate tectonics recycles this carbon. When limestone is subducted, heated, and metamorphosed, it releases company R. This company R is carried by fluids and magmas to volcanic arcs, where it's released at the surface, returning to the atmosphere. The balance between weathering, which removes company R, and volcanism, which releases it, regulates atmospheric company R on geological timescales. If volcanism increases, atmospheric company arises, temperatures increase, weathering accelerates, removing the excess company R. If volcanism decreases, atmospheric company R drops, temperatures fall, weathering slows, allowing company R to accumulate. This negative feedback loop has kept Earth's climate relatively stable, over billions of years, despite the sun becoming brighter over time. Without plate tectonics to regulate atmospheric company, are Earth's climate might have become too hot or too cold for life to persist. But the carbon cycle operates on shorter timescales too. The burial and exposure of organic matter affects atmospheric company R. During periods of high biological productivity and burial of organic carbon, atmospheric company R can drop, cooling the climate. During periods of low burial or increased weathering of organic-rich rocks, company R can rise, warming the climate. Human activities have perturbed this cycle by burning fossil fuels. Carbon that was locked away for hundreds of millions of years is being released over decades. The rate of company R release is far faster than the geological processes that regulate it. The result is a rapid increase in atmospheric company R driving climate change. Other elements also cycle. Nitrogen, phosphorus, sulfur all have geological and biological cycles. These cycles interact with each other, with climate, with tectonics, creating a complex system that connects the solid Earth to the fluid Earth, life to non-life. Understanding these cycles is crucial for understanding Earth as a system. The planet is not a collection of isolated processes, but an integrated whole where changes in one component affect all others. Plate tectonics affects climate. Climate affects weathering. Weathering affects ocean chemistry. Ocean chemistry affects life. Life affects the composition of the atmosphere. The atmosphere affects volcanism through the water it provides. Around and around, feedbacks and connections. A system that has evolved over billions of years. We need to talk about time. Not clock time, not historical time, but deep time, geological time, the time scale on which the Earth operates. This is perhaps the most difficult concept to grasp, the one that requires the most profound shift in perspective. Humans are creatures of short time scales. A human lifetime is about Baz years. Recorded history goes back perhaps Ling years. The entire history of human civilization, from the first agriculture to now, is about Shur Ling years. This feels like a long time to us. It encompasses all of human culture, all our achievements, all our history, but Ling years is nothing to the Earth. It's a blink. The Ice Age, the glacial period that ended about Ling years ago, was itself just one of many glaciations in the current Ice Age, which has lasted about Lok million years. And this Ice Age is just one of several in Earth's history. The dinosaurs lived for about Ibait Losher Wu million years, from Arbike to Loster Wu million years ago. This is so long that the time separating Tyrannosaurus rex from Stegosaurus is greater than the time separating T. Rex from us. The dinosaurs as a group spanned a period of time longer than the entire history of mammals since then. The oldest complex multicellular life appears in the fossil record about Lopbait million years ago. Before that, for over 1 billion years, life on Earth was entirely microbial. Single-celled organisms, bacteria and archaea, living in the ocean, in sediments, in shallow coastal environments. For 3/4 of Earth's history, this was the only life. The Earth itself is Warsi billion years old. If you compress this into a single Ardersuth-hour day with the Earth forming at midnight, the first life appears around CAM. The first complex life doesn't appear until about Jo PM. Dinosaurs appear at Shri PM and go extinct at Shri Scissors PM. All of human history, from the first stone tools to now, occupies the last seconds before midnight. This perspective is humbling. Everything we consider old, ancient ruins, the pyramids, Stonehenge, the earliest cities, all occurred in the last fraction of a second of this cosmic day. The mountains we see, which seem eternal, are young. The Himalayas started forming Worcester's million years ago, a few minutes before midnight in our Arserseeth hour analogy. older mountains have been worn away completely. John McPhee coined the term deep time to describe geological time, this scale that dwarfs human comprehension. He wrote, "The mind is staggered by the concept. Perhaps only in astronomy do we encounter comparable reaches of time and distance." And it's true. The age of the Earth, Sudanwarsi billion years, is comparable to significant fractions of the age of the universe, Bad billion years. Understanding deep time changes how you see the world. That rock in your hand might be hundreds of millions of years old, older than any fossil you'll ever see, older than the mountains around you. The sand on the beach, each grain is a fragment of rock, a piece of a mountain that eroded away perhaps millions of years ago, traveled down rivers, was deposited on a continental shelf, buried, lithified into sandstone, uplifted, eroded again, and finally ended up on this beach under your feet. Nothing is permanent. The continents drift. Mountains rise and erode away. Ocean basins open and close, evolve and go extinct. The surface of the Earth is constantly changing, but so slowly that on human timescales it seems static. We build our cities, our roads, our monuments, as if the ground beneath them will last forever. But it won't. Given enough time, everything returns to the sea, to sediment, to rock, to magma, to new mountains that will themselves erode away. This perspective can be frightening. It suggests our insignificance, the futility of our efforts, the temporary nature of everything we create. But it can also be liberating. The problems that seem insurmountable, the conflicts that seem intractable, are momentary blips in Earth's history. The planet has survived asteroid impacts, massive volcanic eruptions, ice ages, mass extinctions. It will survive us, too. Whatever we do, in the very distant future, the sun will gradually release its outer layers, forming a glowing planetary nebula. What remains at its center will be a white dwarf, a compact, extremely dense stellar remnant roughly the size of Earth, yet containing a mass comparable to the sun. If Earth still remains at that time, it would circle this faint stellar core as a cold, inactive world. Its surface transformed beyond recognition, its oceans long gone, and its landscapes reshaped many times over. Yet this would not mark the end of Earth's physical story. Even as a frozen body orbiting a faint star, the planet would still possess an internal structure, core, mantle, and crust. The dynamic processes that once shaped it would have slowed or ceased, but their traces would remain preserved within the rocks, forming a long record of planetary history. Behind this future feels unimaginably distant, almost abstract, but contemplating it provides perspective. Earth is not permanent. Like all planets, it follows a long trajectory, from formation through activity toward eventual cooling. We currently exist during a rare phase, when the planet remains dynamic, with oceans, atmosphere, and life. But this is a distinctive chapter in Earth's history. Internal heat continues to drive motion within the planet. Tectonic plates still shift. Mountains continue to rise and erode. Life continues to diversify and adapt across environments. This state will not last indefinitely, but it exists now, deigned looking ahead on shorter geological timescales. The movement of continents will continue. Plates will drift, collide, and reorganize. Over hundreds of millions of years, new continental arrangements are likely to form. Based on present plate motions and models of deep Earth dynamics, scientists have proposed several possible future configurations. BAMD-1 proposed scenario, often called Pangea Ultima, suggests that the Atlantic Ocean may gradually narrow, eventually bringing the Americas back into contact with Africa and Europe, forming a new equatorial supercontinent. Another model, known as Amasia, envisions continents migrating northward and merging near the polar regions. These projections remain uncertain. Plate directions can change, new rifts can form, and subduction zones can weaken or disappear. Deep mantle circulation may reorganize over time. Still, what appears consistent is that continental motion will persist, and large land masses will eventually merge again. This repeating pattern of supercontinent formation and breakup has shaped Earth for billions of years and is likely to continue as long as plate tectonics remains active. To understand what drives this motion, we descend to one of Earth's most profound internal boundaries, the interface between the core and the mantle, nearly arjubic kilometers beneath the surface. Here, dense metallic material meets solid silicate rock, marking a sharp transition in composition and physical behavior. Binger, this boundary is complex rather than uniform. Seismic observations reveal variations in structure and properties at this depth. In certain areas, seismic waves slow dramatically, indicating regions of unusual material known as ultra-low velocity zones. These zones may contain partially molten rock or dense material with a distinct chemical makeup. Their origin is still debated. They may represent fragments of ancient tectonic plates that sank deep into the mantle over immense spans of time. Alternatively, they could be remnants from Earth's earliest stages, preserved from a time when the planet was largely molten. Some may result from chemical interactions between the core and mantle at this interface. This boundary remains active. Heat flows upward from the hot core into the cooler mantle, sustaining convection. From this deep layer, columns of warmer material may rise slowly toward the surface, feeding long-lived volcanic hotspots. Features such as the Hawaiian and Yellowstone volcanic systems are thought to be surface expressions of these deep-rooted processes. The temperature at the CMB is about Su Ling to Su Wubak degrees Celsius. The pressure is about Edan Sanlu million times atmospheric pressure. Under these conditions, materials behave in ways we can barely imagine, ways we can't reproduce in laboratories. We infer the conditions from seismic data, from experiments at high pressure, from theoretical models. There's evidence that the inner core is rotating slightly faster than the rest of the Earth, a phenomenon called superrotation. This rotation is driven by the magnetic field and by convection in the outer core. The inner core may also have its own internal structure, variations in seismic velocity that suggest it's not uniform, but has layers or regions of different crystal orientation. Some researchers have suggested that the inner core may even have an innermost core, a sphere at the very center with distinct properties. The evidence is subtle, based on the way seismic waves travel through the deepest part of the inner core, but if confirmed, it would add another layer to our understanding of Earth's structure. The dynamics of the core are crucial for understanding Earth's magnetic field. The geodynamo, the process that generates the magnetic field, depends on convection in the outer core, driven by cooling from above and the release of light elements as the inner core crystallizes. Changes in core dynamics may have affected the magnetic field over Earth's history. The magnetic field has not been constant. Paleomagnetic studies, examining the magnetization of ancient rocks, show that the field strength has varied, sometimes weakening significantly. During these periods of weak field, the planet may have been less protected from cosmic radiation and solar wind. Some researchers have speculated that these periods of weak magnetic field may have affected the evolution of life, increasing mutation rates, perhaps driving evolutionary innovations or extinctions. The field has also reversed many times, the north and south magnetic poles flipping. The last reversal was about Seebi-Basherling years ago. Reversals seem to occur irregularly, with no obvious pattern. Some periods of Earth's history had frequent reversals. Others had long periods of stable polarity. The causes of reversals are not fully understood, but they're thought to result from instabilities in the convection patterns in the outer core. During a reversal, which may take a few thousand years to complete, the field doesn't simply flip instantaneously. It weakens, becomes multipolar with several magnetic poles instead of two, and eventually reorganizes into a reverse dipole. During this transition, the magnetic field is much weaker, providing less protection from radiation. There's been speculation that a reversal might be starting now. The magnetic field has weakened about 500 Sur over the past years, and the North Magnetic Pole has been wandering more rapidly than usual. Predicting reversals is difficult. The field may be entering a reversal, or it may simply be fluctuating, which it does continuously on all timescales. The core mantle boundary is where the solid Earth meets the liquid Earth, where rock meets metal, where slow mantle convection meets rapid core convection. It's a boundary we'll never see directly, never sample, never visit. But through seismology, through modeling, through careful inference, we're building a picture of this remote place, understanding its structure and dynamics, recognizing its importance for everything happening above. Let's shift scale now, from the planet as a whole to the scale of minerals, the building blocks of rocks, the tiny crystals that record temperature, pressure, chemistry, time. Minerals are naturally occurring inorganic solids with ordered atomic structure and definite chemical composition. Every rock is made of minerals, and the identity and arrangement of these minerals tell us about the rock's history. There are thousands of known minerals, each with distinct properties, distinct compositions, distinct crystal structures, but a few dozen minerals make up the vast majority of Earth's crust. Quartz, feldspars, micas, amphiboles, pyroxenes, olivine, calcite, these are the common minerals, the ones you'll encounter in most rocks. Each mineral has a specific crystal structure, an ordered arrangement of atoms. This structure determines the mineral's physical properties, its hardness, its cleavage, its optical properties, its density. When magma cools, atoms arrange themselves into these ordered structures, forming crystals. The size of the crystals depends on the cooling rate. Slow cooling allows large crystals to form. Fast cooling produces tiny crystals, or even glass, where the atoms don't have time to organize into crystals. But minerals don't just form from cooling magma. They also form from precipitation from water, from solid-state transformations under changing pressure and temperature, from biological processes. Calcite precipitates from seawater, forming limestone. Garnet forms when shale is metamorphosed at high pressure. Halite crystallizes from evaporating water, forming salt deposits. The stability of a mineral depends on the conditions of temperature, pressure, and chemical environment. A mineral that's stable at the surface may not be stable at depth. Olivine, common in the mantle, reacts with water at the surface, transforming to serpentine. Aragonite, a form of calcium carbonate, is stable at high pressure but transforms to calcite at low pressure. These phase transformations are crucial in the mantle. As rock descends in a subducting slab, the minerals transform to denser forms, adapting to the increasing pressure. Olivine transforms to wadslite at about Seabyte kilometers depth, then to ringwoodite at about Wubat Arsers kilometers. At about Lobite kilometers, ringwoodite breaks down to perovskite and magnesio-wustite. These transformations are accompanied by abrupt changes in density and seismic velocity, creating the seismic discontinuities that mark the boundaries between different mantle zones. Studying minerals allows us to infer the conditions under which rocks formed. The presence of certain minerals or certain assemblages of minerals indicates specific temperature and pressure conditions. A rock containing garnet, kyanite, and staurolite formed at high pressure and moderate temperature, conditions found in subduction zones. A rock containing olivine and pyroxene formed at high temperature, conditions found in the mantle. Minerals also record time. Some minerals contain radioactive elements that decay at known rates. Zircon, for instance, incorporates uranium but excludes lead when it crystallizes. Over time, the uranium decays to lead. By measuring the ratio of uranium to lead, we can determine when the zircon crystallized. This technique, and others based on different radioactive decay systems, allow us to date rocks, to place events in. Some minerals grow in layers, like tree rings, recording changes in environment as they grow. Each layer may have slightly different chemistry, reflecting changes in temperature, pressure, or the composition of the fluid from which the mineral grew. By analyzing these layers with high-precision instruments, geologists can reconstruct the history of a single crystal. Conditions changed as it grew. Inclusions, tiny bits of other minerals or fluids trapped within a crystal as it grows, provide additional information. A crystal of garnet might contain inclusions of earlier minerals, preserving evidence of earlier stages of metamorphism. A crystal of quartz might contain inclusions of fluid, tiny bubbles of water or brine trapped as the quartz crystallized, providing a sample of the fluid that was present. And minerals are not just geological curiosities. They're economically important. Metals are extracted from ore minerals, galena for lead, sphalerite for zinc, chalcopyrite for copper, magnetite and hematite for iron. Gemstones are minerals valued for their beauty, ruby and sapphire varieties of corundum, emerald beryl, diamond carbon. Industrial minerals provide materials for construction, manufacturing, and technology. Gypsum for drywall, fluorite for steel making, rare earth elements for electricity. The distribution of ore deposits is controlled by geological processes. Many ore deposits form at plate boundaries. Porphyry copper deposits form above subduction zones where hydrothermal fluids concentrate copper. Volcanogenic massive sulfide deposits form at mid-ocean ridges where hot fluids precipitate metals on the seafloor. Understanding plate tectonics and geological processes allows us to predict where ore deposits might be found, guiding exploration. But minerals also pose challenges. Asbestos, a group of fibrous minerals, is extremely harmful to human health, but was widely used in construction for decades. Heavy metals like lead, mercury, and arsenic can leach from rocks and contaminate water supplies. Radioactive minerals like uraninite pose radiation hazards. Understanding mineralogy is crucial for managing these risks, and we focused mostly on the abiotic earth, the rock and metal, and heat. But life, though a thin film on the surface, has profoundly affected the planet's geology. Life is not separate from geology. It's interwoven with it, shaping and shaped by geological processes. And the most obvious impact is the atmosphere. Earth's atmosphere is bifided Arcer-E oxygen, an atmosphere unlike any other in the solar system. This oxygen is produced by photosynthetic organisms, primarily phytoplankton in the ocean and plants on land. Without life, Earth's atmosphere would be dominated by carbon dioxide and nitrogen, with little or no free oxygen, similar to the atmospheres of Venus and Mars. At the rise of oxygen, the Great Oxidation Event about 4.6 billion years ago, was arguably the most important event in Earth's history after the planet's formation. It changed the chemistry of the atmosphere and ocean. It enabled the evolution of aerobic respiration, and it led to the formation of the ozone layer that shields the surface from ultraviolet radiation. It made complex life possible, but oxygen also had destructive effects. It reacted with reduced minerals, oxidizing iron and sulfur compounds. It drove anaerobic organisms into refugia. It changed weathering processes, altering the rock cycle. The planet was transformed by the waste product of tiny microbes. Life also affects the carbon cycle. Photosynthesis removes carbon from the atmosphere, storing it in organic matter. When organisms die, most of this carbon is decomposed and returned to the atmosphere. But a small fraction is buried in sediments, especially in oxygen-poor environments where decomposition is slow. Over millions of years, this buried organic carbon accumulates as coal, oil, and gas, the fossil fuels. Carbonate-secreting organisms, from microscopic coccolithophores to reef-building corals, remove carbon from seawater by forming calcium carbonate shells and skeletons. When they die, these structures accumulate as carbonate sediments, eventually forming limestone. Limestone is one of the most abundant sedimentary rocks, and almost all of it is biological in origin. And without life, the carbon cycle would be simpler, driven only by volcanic outgassing and silicate weathering. With life, carbon is cycled through organisms, creating vast reservoirs of organic carbon and carbonate rocks. Life has become an integral part of the geological carbon cycle. Life also creates rock. Stromatolites, layered structures formed by microbial mats trapping and binding sediment, are some of the oldest fossils, dating back 6 billion years. They're still forming today in certain environments. Coral reefs, built by corals and other organisms secreting calcium carbonate, are massive geological structures, some extending for thousands of kilometers. Chalk, the soft white rock used for writing, is composed almost entirely of the remains of coccolithophores. Microscopic algae with calcium. The White Cliffs of Dover, iconic cliffs along the English coast, are made of chalk formed from coccolithophores that lived in a warm sea about 2 million years ago. Diatomite, used in filters and abrasives, is composed of the silica shells of diatoms, another type of microscopic algae. Even minerals composed primarily of silicates can be influenced by living organisms. Certain microorganisms, including bacteria and fungi, enhance the breakdown of silicate rocks by interacting with their surfaces to access essential nutrients. Plant roots contribute as well, applying physical pressure that fractures rock and releasing compounds that alter minerals chemically. The soil, this thin interface where the solid earth meets living systems, is the result of both physical weathering and biological activity, forming a layered mixture of mineral grains, organic material, water, and air. Life has also played a role in shaping the long-term evolution of Earth's crust. The rise of oxygen in the atmosphere, often referred to as the Great Oxidation Event, may have influenced how tectonic plates behave. As oxygen interacted with oceanic crust, it led to the formation of minerals with different physical properties. These changes may have affected how readily sections of crust could descend into the mantle, subtly altering large-scale tectonic processes. Banned on land, the emergence of complex plants, roughly seaback million years ago, significantly increased rates of chemical weathering. Root systems stabilized sediments, altered soil chemistry, and penetrated deep into rock layers. Through these processes, more carbon dioxide was gradually removed from the atmosphere, potentially contributing to long-term shifts in global climate. Some of the most distinctive geological features on Earth also reflect biological influence. Banded iron formations formed when oxygen produced by early microorganisms interacted with iron dissolved in ancient oceans. Major biological transitions preserved in the fossil record, often associated with volcanic activity, climate shifts, or extraterrestrial impacts, also left clear signatures in sediments and carbonate rocks. Life and geology are deeply interconnected. Living systems rely on geological processes for nutrients, raw materials, and stable environments. At the same time, geological systems are reshaped by life through atmospheric change, carbon cycling, mineral formation, and accelerated weathering. To understand Earth as a whole, both perspectives are essential. And this brings us to the present era, the time of widespread human influence. Many scientists now use the term Anthropocene to describe a period in which Human activity has become a significant factor in shaping Earth's surface and systems. Whether this term will be formally recognized as a geological epoch remains under discussion, but the scale of human influence is widely acknowledged. Physical evidence is substantial. Human activities now redistribute more sediment annually through construction, agriculture, and resource extraction than natural river systems alone. The composition of the atmosphere has shifted, with carbon dioxide levels rising markedly since pre-industrial times. Nutrient cycles, particularly nitrogen, have been altered through industrial processes. Artificial materials and new chemical signatures have been introduced into soils, sediments, and oceans. Landscapes have been reshaped by cities, transportation networks, reservoirs, and engineered waterways. Geologists of the distant future may identify this interval clearly within the rock record. They could observe abrupt changes in elemental concentrations, traces of synthetic materials, and distinctive layers containing industrial byproducts. Fossil records may show rapid shifts in species distributions, alongside chemical markers reflecting large-scale energy use. These signals would form a recognizable boundary within geological strata. What makes this interval unusual is the pace of change. Many geological transitions unfolded over millions of years. The current transformation is occurring within a comparatively brief span of time. Earth systems are adjusting rapidly, sometimes faster than natural feedbacks typically operate. Benda, one of the most visible expressions of this shift, involves climate metering. Carbon that had been stored underground over vast geological timescales has been released back into the atmosphere within a few centuries. This has altered global temperature patterns, affected ice cover, influenced sea levels, and reshaped atmospheric circulation. Other changes extend beyond climate alone. Increased carbon dioxide in the atmosphere interacts with the oceans, modifying seawater chemistry. Nutrient flows into coastal regions have intensified biological productivity in some areas, altering oxygen levels in deeper waters. Large-scale engineering projects have redirected rivers, transformed coastlines, and reconfigured entire landscapes. Together, these changes highlight a new chapter in Earth's story, one in which geological and biological processes are increasingly intertwined with human activity, leaving a clear and lasting imprint on the planet. We're also creating new materials that didn't exist in nature. Plastics, synthetic fibers, new alloys, these are technofossils that will persist in the geological record. Concrete, the most widely used building material, is forming thick layers in urban areas that will be recognizable as distinct strata in the future. The comparison to past mass extinctions is troubling. We're driving species extinct at rates comparable to the 5 great mass extinctions in Earth's history. The difference is timescale. Previous mass extinctions occurred over hundreds of thousands to millions of years. The current extinction is occurring over decades to centuries. The causes are different too, not asteroid impacts or massive volcanism, but habitat destruction, overhunting, pollution, invasive species, climate change, all driven by human activity. And some argue that we're living in a unique time in Earth's history, the only time when a single species has such disproportionate impact on the planet. Others argue that geological forces dwarf human impacts, that the Earth has experienced far worse and recovered. Both perspectives have truth. Yes, plate tectonics operates on timescales that make human civilization irrelevant. Yes, the Earth has survived supervolcano eruptions and asteroid impacts. Yes, the planet will continue long after humans are gone. But the Earth we depend on, the climate we've adapted to, the ecosystems that support us, these are fragile. We're not threatening the Earth itself. We're threatening the conditions that make the Earth habitable for us and for much of current life. The geological perspective offers both hope and caution. It shows us that Earth is resilient, capable of recovering from catastrophes, but also that recovery takes millions of years. It shows us that the current interglacial period, the stable climate of the past, ling years that allowed agriculture and civilization, is an anomaly, a brief warm period between glaciations. It shows us that nothing is permanent, that change is the only constant. But it also shows us that we're living in a special time. The Earth is geologically active. It has oceans and atmosphere. It has life, complex life, intelligent life. This won't last forever. In the deep future, the Earth will be barren, its internal fire extinguished, its surface cold and dead. We're here now in the middle period when the planet is alive. What we do matters not to the Earth as a planet, but to the Earth as a home for life. We're the first species to understand geology, to read the rock record, to comprehend deep time. We're the first species capable of consciously changing the planet's trajectory. Whether we use this capability wisely remains to be seen. So here we are, standing on rock that might be 1 billion years old, breathing air produced by organisms, warmed by a sun that's been burning for billion years, protected by a magnetic field generated in a core of liquid iron ling kilometers below. The ground beneath your feet is not solid, not really. It's flowing, though too slowly for you to notice. It's part of a plate that's moving, carrying you with it at centimeters per year. The mountain on the horizon is rising, grain by grain, pushed up by forces from deep below, even as rain and ice wear it down. The river carries sediment to the sea, where it will be deposited, buried, perhaps in millions of years, uplifted and eroded again. Everything is in motion, everything is temporary, and yet in the moment, it all seems solid, permanent, unchanging. This is the paradox of geological time. On human timescales, the Earth is static. On geological timescales, it's dynamic, constantly changing, constantly renewed. We've descended through the planet, from the surface, through the crust, through the mantle, to the core. We've watched the Earth form from dust, watched continents collide and split, watched mountains rise and erode. We've seen how the internal heat drives everything, how plate tectonics shapes the surface, how life and geology are intertwined. The Earth is not a stage for life. It's not a collection of resources. It's a system, an integrated whole, where the deep interior connects to the atmosphere, where the rock cycle connects to the carbon cycle, where geology and biology shape each other. Understanding this system, seeing these connections, requires thinking across scales, from atoms to planets, across time, from seconds to billions of years. This understanding is both humbling and empowering. Humbling because it shows us how small we are, how brief our existence, how limited our perspective. The Earth was here for billion years before we arrived. It will be here for billions of years after we're gone. We're a momentary phenomenon, a brief flickering in the long story of the planet. But it's also empowering because it shows us we're part of something larger, connected to everything around us, made of the same materials, shaped by the same forces. The iron in our blood was forged in a dying star. The calcium in our bones came from the shells of ancient sea creatures. The oxygen we breathe was produced by photosynthetic organisms over billions of years. We're not separate from the Earth. We're part of it. And now in the early Earth-18th century, we have the knowledge to understand this. We can read the rock record, decipher the story written in stone. We can see back to the beginning, watch the planet form, follow its evolution through time. We can peer into the future, predict what will happen as the Earth continues to cool, as the sun continues to brighten. This knowledge brings responsibility. We understand the consequences of our actions in ways previous generations couldn't. We know how the carbon cycle works, how atmospheric company affects climate, how quickly species can go extinct. We can't claim ignorance. The Earth will continue, regardless of what we do. Plate tectonics will operate. Mountains will rise and erode. The rock cycle will turn. In the deep future, long after humans are gone, the planet will still be here, its surface reshaped by forces we've discussed. New mountains will rise where the Himalayas once stood. New oceans will open where continents now sit. The fire below will continue to burn for billions of years. But the Earth we know, the Holocene Earth with its stable climate and diverse life, this is not guaranteed. We're changing it faster than it has changed in millions of years. Whether future geologists will see the Anthropocene as a brief anomaly or as a major boundary in Earth's history depends on what we do now. And so look at the ground beneath your feet, pick up a rock, feel its weight, its texture. Know that it's older than you can imagine, that it's traveled a journey from deep within the Earth, that it carries a story encoded in its minerals, its structure, its chemistry. Know that you're standing on deep time, on a planet that's been here for billion years and will continue long after you're gone. And know that you're part of this story, not separate from it, not above it, but woven into it, connected to the rock and the water and the air. We're made of earth, shaped by earth, dependent on earth. Understanding this, feeling it, not just knowing it intellectually, but feeling it in your bones, this is what it means to have a geological perspective. The eternal fire still burns below. The plates still move. The mountains still rise. The planet is alive, geologically speaking, and will remain so for billions of years. We're fortunate to be here now, in this brief moment when the Earth is both geologically active and inhabited by intelligent life. Let's not waste this moment. Let's understand where we are, what we're standing on, what forces shape this world. The Earth has a memory longer than life itself. It has witnessed everything, and tonight we've listened. We've heard the story of rock and fire, of creation and destruction, of forces operating on scales beyond human comprehension. This is the story of the planet we call home. Well, thank you for descending with me into the depths, through deep time, to the core of the Earth, and back again. The ground beneath your feet will never seem the same. And perhaps that's exactly as it should be,